And this current transfer is expected to connect with the burdens with 5 watt amperes. All right. So let's say this is a relay giving us a 5 watt ampere. So this 5 watt amperes of burden to this current transformer can be translated in terms of impedance in the values of 5 ohms. So how actually I can find this 5 ohm values here? So now let's say if you refer to this diagram, right? So we are having a current transformer. So this is the current transformer. The secondary current rated at 1 amp, which means that the secondary current flow here is 1 amp. And the power produced here at the secondary side, let's say with this relays being connect, this is the apparent power absorbed by this relay, so which is 5 watt ampere. So first thing first, we want to find what is the voltage drop across the secondary winding, which is across this relay here. So we have the power, we have the current flow, right? So by having the power divided with current, right, you can find what is the voltage drop across this relay. In this case, is 5 watts. But this is still not the impedance value, right? So I not want to find what is this relay's burdens value in the units of ohm, right? How actually I can find this? So with the voltage drop across here is 5 watt and the current flow is 1 amps, right? So you just use the Ohm's law of 5 divided with 1 amp, so you know that the burdens due to this relay in terms of impedance, it will equivalent to 5 ohm. Okay, so that's how we convert from burdens reading in apparent power to the units of ohm in terms of impedance. So what happens if, let's say, I'm having a same relay, all right, with this burden 5 watt ampere, but this time I change the current transformer and its secondary current is rated at 5 amp instead. This is 1 amp, this is 5 amp. So with the same burdens rating for this relay at 5 watt ampere, whenever we change the current transfer, you will notice that in units of ohm, which is in terms of impedance, right? This 5 watt amperes burdens from this relay is actually equivalent to 0.2 ohm, which is not the same as the first case here. So how actually I can get this using the same way? So now whenever we have this current transfer being used, this time the secondary current flow is 5 amp, okay, standardized at 5 amp. We know that this relay giving us the burdens in terms of apparent power is 5 watt amperes, right? So P is equal to VI actually. So you can actually find the voltage drop across this relay here by having the power divided with the current flow, secondary current flow, all right? So the voltage drop across this relay is 1 watt. Okay, after this, just use the Ohm's law. The current flow will not change, standardized at 5 amps, right? So 1 watt divided with 5 amps. So you will find now this relay will give us the impedance value at 0.2 ohm instead. So you can see, right? Yes, I have this burden due to this relay in terms of apparent power is 5 watt ampere, but it's not always the same in the units of ohms for impedance. It's actually depending on what is the current transfer you are using. Is secondary currents value standardized to what value? Is it 1 amp or 5 amp? And you also notice that if you're comparing these two values here with the same relay being used, so whenever we increase the secondary currents rated value, you will notice that the burden in the units of impedance is actually reduced. All right, so that is what we can see here, and you can actually see how actually we can change from watt ampere to impedance. All right, so now let's move on to the next slide here, where we have one table showing a current transformers with its secondary currents rated at 5 amp. How actually we can interchange the burdens from watt ampere, which is apparent power, to impedance value in the units of ohms. All right, so you can actually practice on your own how actually you can convert here to here. So the tips for you is refer to the previous slide using the Ohm's law. In the event, if you want to change from power to the units of impedance, remember, divide the current 2 times. divide the secondary currents 2 times. Like this case here, 0.05 divide with 5 square, you can get this value. Okay. In the event, if you want to convert from units of ohm to watt ampere, do reversely multiply the secondary currents values here 2 times. All right. So that's how we do the interchangeables of the burdens from apparent power to impedance or reversely. Okay. So now continue in this slide here. So if you look into these diagrams, right, we can say all the burdens is actually connect in series connections at the secondary terminus of the current transformer. So whenever we increase the burden, which in turn you increase the impedance, all right? So we actually are causing the wrong operations of the current transformer. So what happens if I have unloaded current transfer? Not loaded, which means that this is the secondary side of the current transfer is become short circuit conditions. Do you still remember? Just now we have proved it. In the event if I short circuit here, right? So there will be no issue, all right, from this current transformer. So the power as well as the induced voltage is actually equivalent to 0. Do you still remember this? So Z equivalent to 0. P is I square R, right? So P is 0. Voltage drop based on Ohm's law, all right, also 0 as well, all right, IR, all right, so the impedance here is 0. So watt ampere burdens is 0 because the voltage here is 0 under unloaded condition, short circuit scenario. All right, so this current transfer being used has to be cross-checked if it's able to drive all the attached burden at its secondary side without turn into saturation zone even under fault conditions. So the areas of the current transfer is actually depending on the total burdens, remember? So basically, we can also say that the areas coming from the current transfer also depending on the phase angles of the burdens as well as its magnitude values, right? So now let's see how actually we can find the total burdens that can be attached at the secondary side of the current transformer. So to do so, we will move to the next slide here. We have to use the equivalent circuit of the current transfer. So we want to analyze if this current transformer able to withstand the burdens that's being connected at its secondary side. So if you cross-check with these diagrams here, this is the equivalent circuits of the ring type. Ring type is actually one primary types of current transformer. Where the left side here, we have primary winding, all right? So it will connect in series with the power line. And then at the right-hand side here, we have secondary winding. So this secondary winding will connect with the burdens or any other device that we need to connect here for current measurement. So whenever we have primary current flowing through the primary winding here, so now the flux actually generates. So with such a case, it will induce the magnetizing current flow, all right? So this magnetizing current, IE, will flowing through the exciting impedance here. So usually this impedance value is very large in order to have low magnetizing current for the ideal current transformer. So what is this I2 value? So whenever we have loads being connected at the secondary side, there will be secondary current flowing through all the burdens that's being connected at its output terminals, including the internal winding resistance at the secondary side. So RCT is secondary winding resistance. The numbers of winding turns, yes, it gives you the resistance value, as well as the burdens in terms of resistance, in terms of reactance as well. Let's say this is not a pure resistive load. All right, so next one we have V2 and VB. What is this here? VB is the voltage drop across the burdens. V2 is the voltage generated at the secondary side. All right, so you can see usually these two, the value is the same because this path, they are in parallel connections. So let's move on here to the next slide here. So for current transfer, it's same as any other principles of the transformer. The ampere turns at both sides should be equal. All right, so let me draw your attention by looking into this dialog box here. So whenever we have ideal transformer, which means that we have no power loss. So the power generated at both sides the primary circuit and the secondary circuit here would be the same. So if you expand in terms of power, right, for this equation, as the apparent power can be found with the product of voltage and current. Subscript 1 here indicate that this is the parameters you obtain from the primary side. This is from the secondary side. No power loss that will be equivalent to each other's. So if we rearrange this in terms of ratios like this for an ideal transformer, so the ratios of primary voltage to secondary voltage will be same as the primary winding turns divided with the secondary winding turns, and hence is also equivalent to this, the ratios of secondary current to the primary current. That is actually the equations for an ideal transformer. So if you cross multiply in terms of ampere turn, you will notice that N1 I1 will be equivalent to N2 I2. That is for ideal transformer. But in practice, right, there will be small magnetizing current flow, remember, at the secondary side. So let's check out the first point here. So for a practical transformer, the current transfer at the primary ampere turns here would be equivalent to the secondary ampere turns with the magnetizing ampere turn. So N1 I1 is equal to N2 multiplied with summations of I2 plus IE, which is actually here secondary current flow and the magnetizing current. Okay, because of this magnetizing currents here, causing us to have a low efficiency of current transformer. So they are not the same anymore. They are not the ideal transformer. But in practice, right, usually this current, the magnetizing currents here, the magnitude is very small as comparing to the secondary current flow. So usually for the calculations that involve the current transformer, we will ignore this, treating it as an ideal transformer, except we have the constant in terms of ratios current as well as the phase angles errors. Okay, so moving on here to look into this magnetizing current, which is flowing through this path here, you will notice that this current's magnitude is actually depending on the secondary voltage, which is generating here. And we know that this path is actually in parallel connection. So we can say V2 is actually same as VB. So if we want to change this magnetizing currents value here, we need to change the secondary voltage, in which this secondary voltage can be found by having the secondary current flow here multiply with all the burden that's being connected at the output side. It's just the ohms law. I multiply with Z here, where the Z we have in terms of real number, we have internal winding resistance, add with the resistance due to the burdens, and then add with the reactance in terms of imaginary numbers. We have reactance due to the burdens. So in order to control these magnetization currents here as small as possible, we have to control the resistance value here, and hence we can change these V2 or VB values right now. Okay, so right now if we move on to next slide here. So during linear operations of the current transfer, which means that we have unsaturated regions right now, the magnetizing currents will be very small as comparing to the secondary currents, and this is only true up to the knee point of the magnetization curve as what we have seen just now. Right, so under this situation, if we have a linear response of current transformer, the ratios of the phase angles errors here will be very small, which indicate that we are able to maintain the primary and secondary currents relationship, or I should say, I can get the correct reading if I have the current transformer operate under unsaturated regions. So the current transformer cord doesn't turn into saturation mode. So let's check out an examples here, how actually I can find the total burdens can be connected at the secondary side. And you will need to cross-check with the knee point voltage to see whether it's still able to work in proper manner by using the current transformer equivalent circuit. So now let's check out the descriptions here. Suppose right now you are being given a current transformer and it has the secondary current rated at 1 amp. So for this current transformer, it's being configured with the secondary winding turns, right? And this secondary winding turns give us the internal winding resistance at 1 ohms. And then we have a burdens being connected at the secondary side. You can see is pure resistive loads with 7 ohm. The reactance value is 0, right? So let's say the knee point voltage of this current transformer is 150 watts. So which telling you that the maximum voltage for the current transformer to be operate at the secondary side should keep lower than this voltage value. Higher than this, it will enter into the saturation regions. Now let's see, with these situations, we have this current transformer and with these burdens here, with the knee point voltage being given, what would be the secondary current flow, the maximum value? Okay, so now my intention is to find this I2 value. So the maximum voltage can be generated at the secondary side is 150 watts. So it's just based on Ohm's law to find what is the current able to flowing through for all of these burdens being attached. So we will have 150, which is the knee point voltage, the secondary voltage, divided with all the burdens that's being attached. So including the 1 ohm from the internal winding resistance add with 7 ohm coming from this burden. Let's say this is relay. The relay is pure resistance. So 150 divided with 8. So you know that the maximum current can be flowing through with this connection, with these burdens numbers here, is 18.75 amp. Okay? So what happens? I want to have this current transformers here work for protections purpose. So I want to maintain the linear response from this current transformer up to 20 times of the current transformer's rating. So 20 times of 1 amp, which means that I'm expecting to have 20 amps being flows here. So what would be the total burden can be attached at the secondary side in the event if I have fault situations with 20 amp flowing through at the secondary side. So this point is mentioned that if we have this situation, the fault that causing the secondary currents here at 20 ampere, the double burden should be connected less than 7.5 ohm, else it will turn into saturation mode. So how actually I can get this value there? It's the same, also based on Ohm's law. So in order to get what is the burdens value based on Ohm's law, so I know that the maximum voltage will be the knee point voltage, so which is 150 watts, all right, at the secondary side. I will need to divide with the current flow. In this case, it say 20 times of the rated current at the secondary side, which is 20 amps. So 150 divided with 20 amps. So the burden that can be attached at the secondary side with these situations is actually only up to 7.5. So you can see, right, initially I have 8, right? If I'm expecting the currents much more higher flow at the secondary side, the burdens value have to become lesser by 0.5 ohm. So from this example, right, you can see in order to have the current transfer able to measure much higher current value, in this case 20 times higher as comparing to normal conditions, we have to ensure that the burden placed here should be as low as possible, lower than 7.5 ohms, so that it will not turn into saturation mode. Are you okay? So from here you can see how does the burdens causing the current transformer here able to work correct manners or not. So now let's move on here to the next slide. All right, so the rules of thumbs regarding to the correct operations of a current transformer, remember, this current transfer should not turn into saturation mode. So we have to keep the secondary voltage at its output terminals here doesn't exceed the knee point voltage value. And this knee point voltage we can obtain from the magnetization curve, remember? And what else we need to make sure is the magnetizing current here should be as small as possible so that it will not cause the errors measurements from the current transformer. So with such a case, right, the specifications of the current transformer is usually being given in terms of knee point voltage. So it will telling you what is the maximum voltage can be induced at the secondary side, as well as what is the magnetizing current at the knee point or at any other point. All right, so you will know it doesn't causing it to be having a wrong operations, as well as the secondary resistance. Right, we know that due to the internal winding turns here, if you have this resistance value, we have to consider this internal winding resistance here as the burdens as well. So the spec of the current transformer should give you this kinds of parameter: knee point voltage, magnetizing current, as well as what is this internal winding resistance. So now, whenever we have high measurements of currents being used, right? Let's say we want to measure a high current value. So which means that we will apply a protection class of current transformer. We have to keep the internal winding resistance values here as small as possible. As we know, whenever we have current flowing through the wire, it will generate the copper loss. So we want to limit the copper loss here and hence result no heating to this current transformer. So how we can ensure this? So whenever you want to get the high current measurements, always keep the burdens here as low as possible. So that's basically the tricks behind. Okay, so as a recap for you, what is actually a knee point? Knee point is a point where we can get on the magnetization curve of the current transformer, in which any increments in terms of voltage right now, let's say 10% here, will produce 50% increments in terms of magnetizing current. That is the definitions of the knee point voltage. All right, so now let's move on to the next slide here. So how actually we can do the correct selections for the current transfer. So depending on the applications, so it's important for us to consider the different factors, including what is the burdens to be connected at the secondary side, the first factors here. The other one, what would be the modes of operations for these protections? This is the second factors. The third factors to be considered as well will be what would be the change in terms of impedance value over the range of the relay settings, rather than just considering what kinds of device you will connect at its output terminal, which is at the secondary side. So you can see we have 1, 2, 3 factors to be considered whenever we want to ensure the current transfer give you the right measurements. So take note that different setting for the relay will give us different burdens value in the units of impedance ohms. So let's refer an example here. How does the relay settings affect the burdens values? So now, if you are being given a current transfer right now, and then the secondary current has been rated at 1 amp, and this current transfer is expected to connect with the relay with the burdens of 3 watt ampere. Right? This is in terms of apparent power. So what happens if this relay, let's say it's an overcurrent relay, it has been tuned to pick up at 50% of the settings, right? So 50% of the setting would be based on this secondary current flow here. So 50% of 1 amp will give us a value of 0.5 amp. So in the event, if the current flow through the primary circuit causing the secondary current flowing through the relay higher than this number, this overcurrent rate will start to react. All right, that is what we consider as a fault conditions. So what happens if you have 50% of settings right? What would be the burdens for this relay in terms of impedance? So as what we have seen just now, converts from apparent power to the units of impedance, right? First thing first, has the power divided with the current flow at the secondary side. So with 50% settings, so we are expecting 0.5 mR is the secondary current flowing through the relay coils right now. So with such a case, the voltage drop across the relay coil would be 6 watt. So after this, we want to convert these settings here in terms of impedance, right? So with the values of 6 watts being dropped across the relay coil, and we know the current flows in this case is 0.5 amp. So 6 watt divided by 0.5 amp based on the Ohm's law, we will notice that right now with 50% setting for this overcurrent relay, it will give us the burdens value in the impedance of 12 ohms. So what happens, I change the settings right now. Instead of 50%, I have it to be picked up at 200% instead. Alright, so 200% of 1 ampere. So this indicates that the secondary current flowing through the relay coil with this setting is 2 ampere. Okay, so same, we'll find what is the voltage drop across it. So with this burdens in the apparent power, 3 watt ampere, divide with the secondary current flow with this setting, which is 2 amp. The voltage drop across is difference, you see, is at 1.5 watts. So to find the impedance value, so same Ohm's law, 1.5 divided with 2 amp. So I know that with this settings for the overcurrent relay, this burden will give me the impedance in the values of 0.75 ohm. So you can see, right, this impedance value doesn't stay the same in the units of ohms here. It's actually changed based on what is the setting for this relay. The higher the setting would be, as you can see, the lower the impedance would be for this relays right now. Okay, so if let's say I will want to have the current transformer, this current transformer to pick up these two situations, all right, I'm considering I will have the relays pick up from 50 up to 200%. I will do the change in terms of setting. So how actually I can determine whether this current transformer is able to work or not. So now let's move to the next slide here. So what if I want to maintain the characteristic of this relay up to 20 times of the relay settings, right? So 20 times bigger right now considered as a fault. So I want to find what is the knee point voltage I should select for the current transformer. So in the event I want to have 20 times of the relay setting, so if I have 50% setting, remember, the voltage drop across is 6 watt. So 20 times bigger, so I have 6 watt multiplied with 20. So I'm expecting that the voltage drop at the secondary side will be 120 watts if I have setting at 50%. So what happens if I have 200%? So same, voltage drop across it multiplied with 20 times, since being mentioned here. So 20 times 1.5 here. So in this scenario, if I have fault occurs, the secondary voltage will having this value here at 30 watt if I have this relay being tuned at 200% setting. So now I want to select the right current transformer so that it can give me the correct readings with these two relay settings. So remember, I should have the knee point voltage value here, right? All right, being set as the maximum voltage that can be generated. So now I would like to ask you this question: how actually I can select? So should I select based on 50% setting, or I should set based on 200% setting for the knee point voltage of the current transformer? Anyone would like to try? If I have 50% setting, the voltage generated at the secondary side is 120 watt. If I have 200% setting for a relay, I will have voltage as 30 watt. So in order to ensure the current transfer select is able to measure correctly, I need to find a right knee point voltage value. Should I select based on 50% setting, or I should select based on 200% setting? So anyone would like to try? Hello? So the knee point voltage value is the maximum voltage can be induced at the secondary side. So in such a case, if you want to have the relay to work up from 50% up to 200% setting, right? The answer you can find here, right? So it says that I should select based on the lowest percentage setting. Why? Because you can see, right, if I have it tuned at 50%, the secondary side, the wattage there is 120 watts. If I have 200% setting, the wattage at the secondary side is 30 watts, right? So if I want to set the maximum voltage can be generated for this current transfer, I will base on the low setting here, where the knee point voltage set at 120 watt. Why? So let's say you choose based on 200% setting, and the maximum voltage is 30 watts only, right? So what happens if you change the setting to 50%? Hey, then this secondary voltage now is 120 watts, which is higher than the 30 watts right now. So with this scenario, right, if you want to have overcurrent relay to be tuned and booked to pick up the fault from 50% to 12%, you have to choose the knee point voltage value based on the low setting, because we're expecting to have much higher voltage right now at the secondary side. Are you able to understand this? Hello? Okay, so that is based on the percentage. So do you still remember another factors to be considered during the times of selecting the current transfer will be based on what is the moods in terms of operations. So you want it to be pick up over current conditions. Let's say you also want it to feed it to a fault relay as well. So this current transfer is responsible to give the current reading to these two relay, over current relay and fault relay. So we have two protections in terms of operations right now for the current transformer. So let's say the current transformer is need to connect with the earth fault relay right now. And this earth fault relay having the same burdens in terms of appearance, let's say at 3 watt ampere, same as the overcurrent relay. So I have two relay to be connected with this current transfer for the measurements. So in the event, if I want to have this earth fault relay here being tuned at 20%, right? So 20% of this current transfer, let's say I'm using this current transformer. This current transfer to be connected with two relay. One is overcurrent relay, another one is a fault relay. Both relay give me the burdens rating in appearance power is 3 watt amperes for example. So just now, right, this slide said that if I have the earth fault relay being set to pick up at 20%, so 20% of rated currents at the secondary side of the current transformer would be 20% with 1 ampere is actually 0.2 amps, right? So this 0.2 amp will flowing through this earth fault relay operating coin. So this is the burdens in terms of appearance power for the earth fault relay. So I want to find what is the voltage drop across this earth fault relay, right? Under these situations, 20% setting. So 3 watt ampere divided with 0.2, 20% of 1 amp. That's how I get 0.2 amp. So you'll find that the voltage drop across the earth fault relay, right, will be 15 watts. Okay, so what would be the impedance value with this setting? Same, Ohm's law, 15 watts of voltage drop across it divided with the current flow. So this earth fault relay will give me the impedance of 75 ohms. So what if I want to have this earth fault relay here to maintain is a characteristic up to 10 times of the relay. So same, this 15 watts have to multiply with 10 times. So right now, how actually I can choose the knee point voltage of the current transfer, considering if this current transfer have to cater for earth fault relay to be picked up at 20%, as well as overcurrent relay with this 50% and 12%. So you know that if I'm considering based on overcurrent relay, the maximum voltage produced is with 50% at 120 watts. But what if I also connect it with the earth fault relay with this setting, 20%, all right? So we know that the voltage is 50 watts. So under 10 times of this ratio is 150 watts instead. So if you comparing this 150 and this 120. So this time I will base on the fault relay instead to pick up what is the voltage should be selected for this current transformer here in terms of Nipah voltage. So instead of 120, I will choose 150 instead. Because even though I have this setting here, the voltage induced at the secondary side will not exceed 150 watts from these fault protections. Are you okay? So you can see based on what is the operations in terms of protections you want this current transformer for the current measurements, it will actually change the knee point voltage selections as well. Okay, so now let's move on here to the next slide here. So we know this is the equivalent circuits for a current transformers, right? So we can have another forms of equivalent circuit for any kinds of transformer. So we can actually obtain this one from here. So how? Is by eliminating the transformer. This is the transformer we have. We want to remove these transformers here from the equivalent circuit so that we can able to analyze the circuit in much more easier manner. So how we can do this is by relocating the load, right? Or I should say reflect the load. Reflect the primary circuit to the secondary side. So for whatever that has been connected here at the primary side, it will be need to convert it to the secondary side. How we can do this is by having the primary loads here, which is ZE, multiplied with turns ratio squared. N is the turns ratio. N1 divided with N2, or V1 divided with V2, or I2 divided with I1. All right. So that is how I do the relocations of the loads at the primary side to the secondary side. Okay. So for the loads that initially at the secondary side, right, it doesn't change. All right. So it stay there. This is the burdens resistance. So this is the resistance due to the internal winding resistance. It doesn't change. What is changed right now is those loads that locate at the primary side. I want to relocate or transform it to the secondary side. That's how I eliminate this transformer in the circuits right now. So with such a case, it's much more easier for the analysis. So you will notice that this is ZE, which is the excitations impedance, where the magnetizing current flow, IE, or I have it at IMs, all right, flowing here. This is where the secondary current flow bring through all the burdens that's being placed at the secondary side. So right now, the primary side will consist of the current source right now, all right? So current feeding in here split into two, the secondary current flow as well as the magnetizing current. So with such a case, it's much more easier for us to do the analysis for the circuit that contain the transformer. Okay, I'm not sure you learn about this or not, the relocations of the loads from primary side to secondary side. Or you can do reversely, from secondary side to primary side to remove the transformer. Okay, so now let's move on here to the next slide. So with this equivalent circuit after removing the transformer, so we know that with the fact where the area of the current transfer is actually come from the magnetizing current. And do you still remember this magnetizing currents here can be found by having a nodes being applied here. So we know that after the relocations of the loads from primary side to secondary side, the primary currents here for in terms of impedance, we multiply with turns ratio square. For the current flow initially at the primary side, we will need to divide with the turns ratio. So if you apply KCL nodes here, right, if let's say you want to find the primary currents models, the entering current is equal to leaving current, right? So IP over N is equal to IE plus IS, the secondary current flow. So removing these turns ratios here by bringing to the right-hand side, so you'll notice that the summations of primary currents and magnetizing currents here need to multiply with turns ratio. Okay, and we know that for this magnetizing current here is actually depending on the secondary voltage induced at the secondary side, and this voltage will cause the secondary current flowing through all the burdens. So we know that to change this voltage value, we are able to change the currents that are directly proportional to each other, in which to lower down the magnetizing current, I will try to lower down the voltage induced here, which is by lowering the secondary burdens value. So what we can say, if you look into this another form of equivalent circuit for the current transfer, we can also try to lower down the areas coming from the current transfer by reducing the burdens here. Because the higher the burdens will be, we know the higher the area will be for the current transformer. So with such a case, the impedance here from the connected loads should be kept as low as possible to avoid the current transfer turn into saturation mode due to the magnetizing current flow here. So usually we want to have this value here as low as possible. Okay, so now let's move to the next slide here. So in a summary, so how actually we can deal with the problems for the saturations of the current transformer. So it's based on the parameters that relates to this, all right, the saturations. So we know that the error is coming from the magnetizing currents, right? So first way to remove the error due to the saturations of current transformer is by changing the cross sections areas of the current transformer's core. So this core is with a specific dimensions, right? So with these specific dimensions of a core, is able to store an amount of the of the flux. So if we are able to increase the areas of the core, let's say it's the iron core, we can actually have the ability to store much higher flux being generated right now, so it will not turn into saturation mode. So one way to eliminate the current transformer turn into saturation mode is by using a bigger areas of the core for the current transformer. So this is the first way. So the other ways, right, so also due to the materials of the cores right now, other than changing the area, we can use different material, right, where we want to use the material with high permeability, which means that it's able to store much higher magnetic fields right now. So with such a case, it will not enter into saturation. So from these two parameters here, you can see the core of the current transfer plays an important role to stop the current transfer turn into saturation mode. So have it to be much more bigger, or you use the material can store much more flux or magnetic fields. Okay, and the other ways here is what we always keep on mentioning. So we want to reduce the burdens that plays at the secondary side. So the burdens here we have will be the resistance coming from the relay or coming from the connecting leads, as well as the internal winding resistance. So usually we will limit the external load being connected at the secondary side of the current transformer. That's how we reduce the burdens, right? So usually these lead burdens here can be further reduced if we are using a much lower ratings of current transformer at the secondary side, right? So this is a three-way for us to stop the current transfer turn into the saturation mode much more easier, all right? So now let's move on here. In addition to burdens being connected, what is the modes of operations? Is it you are having it to pick up the overcurrents or the earth fault situations, even considering how does the value change for the impedance for the burdens based on the relay pickup values? It's also very important for us to ensure that the current transformer is able to operate under both normal conditions as well as fault conditions, all right? As we know, current transfer is in series connections with the power line, right? It should be able to take the fault currents value, and it should not turn into saturation mode, right? Once by making sure the error doesn't exceed its acceptable limit. So there are actually two simple procedures here to confirm or to ensure if this current transformer's error here doesn't exceed its limit. So how we can do this? So the first step here, so by having the selected current transfer in terms of primary rating, what is the current flow under normal condition, it should be more than the expected full current value. That is the first step. So the second step here, so we know that the current transfer will be connect with the burdens, right? We have to ensure that this current transfer able to work under worst case situation, which is with fault current flow. So now how we can do this? Of course, you need to find what is the total burdens value at the secondary side. So after this, with this burdens value, we try to find what is the secondary voltage generated whenever we have fault situations. So now with this voltage being determined, after this, you have to cross-check with the knee point voltage value, which you can able to extract from the magnetization curve again. If this worst case situations with fault conditions, the voltage induced at the secondary side is higher than the knee point voltage. So sorry, this current transfer selected is not suitable. Why? It will enter into saturation regions. But if we have the induced secondary voltage here under worst case situations, with this voltage value is lower than the knee point voltage, yes, this selected current transfer is the right one. So there will be no saturations occurs. So that's how we ensure the current transfer able to work for a specific system. All right. So now let's move on to look into these examples here. So we want to see if this current transfer able to work or not. Is it suitable for this specific power system networks? So for example, if you are being given a current transfer with these specifications, where the rated current ratios here, the CTR is 500 to 5. This is the primary currents. This is the secondary current. So from here, you can find what will be the current transfer ratios by having 500 divided with 5. And then for this current transfer with its secondary winding turns here, it gives you the winding resistance value at this 0.242 ohms. And then for this current transfer has been configured with steel core. And this steel core with the areas at this in the unit meter square, 0.00193. All right. And for this current transfer with these areas of steel core, the maximum flux density it can store is 1.2 Tesla. So this is the back specs of the current transfers we have. So you want to have this current transfer connect to this electrical power system, operate at 60 Hz for current measurements. And we're expected that if we connect with the burdens with the total impedance of 0.351 ohms, is already in the units of ohms. So we want to see if this current transfer able to operate correctly or not in the situations with the anticipated rated current values at 10 kiloamps. This is flowing at the primary side. So does this current transfer will be saturated or not? If we apply to this system with the current to be measured at 10 kiloamps. So here is the curve that's been given to us, the magnetization curve here. So obviously you have to find what is the knee point voltage, what is the secondary voltage induced, then you can cross-check whether this current transfer enter into saturation modes or not. So for your information, there's two ways for us to solve this example. All right, so I will show you the solution in this slide here. One way is by using the magnetization curve. Remember, this one is being given to you. So you have to find what is the voltage induced at the secondary side with these situations, 10 kiloampere flow, all right? And then find what is the knee point voltage based on the current transfer ratio, like this case here at this point, and cross-check whether this voltage at the secondary side is higher or lower to see whether it's entered in the saturation mode or not. All right, so now in such a case, we have to find what is the voltage at the secondary side. Okay, to find the voltage at the secondary side, if you look into the equivalent circuits here, to find the voltage here, right, I need to know what is the secondary current as well as what is the burdens value we have in terms of resistance value or impedance value. All right, so to find the secondary current value, we know that this current transfer will connect with the system and expecting to measure the current at 10 kiloamp. this 10 kilo amp is the primary current. So how actually I know that what would be the secondary current value here for this particular 10 kilo amps value for this current transfer is based on CTR, the current transfer ratio. So we know that CTR is equal to primary currents divided with secondary currents, right? So I can rearrange in terms of secondary current. So I have the primary current, which is 10 kilo amp, divided with the ratio, the current transfer ratio is 500 divided with 5 here. So you know that the equivalence value of 10 kilo amp in primary side will be stepped down to 100 amp. So flowing through the loops right now. So after you find the secondary currents, you need to multiply with all the burdens value based on Ohm's law. So burdens multiplied with the current. So what would be the burdens we have? So for a question, it states that the burdens impedance we have is 0.35 ohms, right? But don't only take this as the burdens. Remember, the winding resistance at the secondary side for the current transfer also considered as the burden as well. So you have to add these two together. So this value is 0.242. Add with the burdens value here, pure resistive at 0.351 as a total burdens connect at the secondary side. So after you multiply with 100, so with these situations, 10 kilo amp to be measured by this current transformer, it will actually induce the voltage at the secondary side here at this value, 59.29 volts. So after this, I need to find what is the midpoint voltage for this current transformer. So I have enlarged the magnetization curve for easier analysis. Okay, so from the question it stated that I has the current transfer with the ratios of 500 to 5, right? So here I have 600 to 5. The second line is 500 to 5. So which means that I have to refer to the second line here. All right, and look for what is the midpoint voltage for at this particular point. So just now I have found that with these situations, 10 kilo amp being measured by the current transformer, the voltage generated at the secondary side is 59.29, right? Which is close to 60 volt, correct? So now here is the voltage value at the secondary side. This is the magnetizing current, okay? So now with the value close to 60, so 10, 20, and then you count up to 60 here. So if you draw a horizontal line here, you will notice that 60 volts, which is the secondary voltage induced at the secondary side, is actually slightly lower than the midpoint voltage. So with such a case, we fulfill these situations where this current transfer will not turn into saturations. But why? With the voltage induced at the secondary side right now is actually lower than the midpoint voltage. So this is the first way for you to solve this example. Okay, and we have another way to solve this examples here is by using this, the transfer equations. Remember, we have 4.44 multiplied frequency, areas of the core, turns ratios, and then the maximum flux can be stored. So seeing as we have the steel core area given in terms of meter square, unit SI, and the maximum flux can be stored in units of Tesla. So we can make use of this formula to see in the event if I has 10 kilo ampere is being measured, what would be the flux being generated? And then I compare with this, the maximum flux can be stored. In the event if this value here is less than this, which means that it will not turn into saturation mode because this is the maximum flux it can store. If this flux right is higher, then it will enter into saturation mode. That is the second way we solve this example. So let's see the solutions here. So in order to find what is the magnetic field generated whenever we have 10 kilo amp to be measured, we need to know what is the voltage induced at the secondary side. All right. So as already demonstrated you how to find, right? So we will have the secondary currents multiplied with burdens, and the current can be found through using the current transfer ratios as well as the primary currents, right? So this is actually same as how we found here. So we know that the voltage induced at the secondary side with the situations if we are measuring 10 kiloamps is actually close to 60 watts, right? So this 60 watt will be the secondary voltage to be substituted here. So what will be the operating frequency? 60 hertz put here. What is the areas of the core? 0.0193 meters squared put here. How about N is the turns ratio? 500 divided by 5, put it here. Then you can find what is the magnetic field is being generated right now. So if we are measuring the 10 kiloamp, so it will be at 1.15 Tesla after you press your calculator, of course. So after this, you cross-check with this. This value is lesser than the maximum flux density can be stored, so which indicate that the current will not turn into saturation mode. So this is the second way for you to solve these questions. You can either use the transformer parameter to solve it, or you can use the magnetization curve to compare with the knee point voltage. So in the event this one is not being given to you, then we solve using these formulas here. Okay, so now let's move to another topics also regarding to how we select the current transformer to be used. All right, so now these are the factors you have to assess, all right, whenever you want to select the right current transformer to be applied for the power system. So first one will be in terms of accuracy class. This is defined by IEC standard. Then another one will be what would be the secondary rated current value, 1 amp or 5 amp. And the third one here we have accuracy limit factors, in short is ALF. And next one here we have what is the short time current rating for this current transformer, how long it's able to withstand